So this is for the other configuration. It's not exactly the same equations, but very, very similar. Come on. Right. If we talk about the forces that are calculated, because basically that's what we wrote on the board before, we calculate resulting forces in the directions of the frame of the drone. So here we'll have basically a UW, so a force in the W direction of the drone. So this is on the drone frame, right? So this moves together with the drone, right? And we calculate it based on the forces that are also moving with the drone. So we don't have any transformation happening here. So we'll have basically the forces, all the lifting forces from all the motors. It will be the sum of them. For this configuration, the torque or the input for the P direction, because I have a rotation here, so it's a torque, it will be basically the imbalance between these two motors, right, F4 and F2, times this length. This is the length that connects the axis of rotation of the motor to the center of gravity, right? While for the other direction, it will be the difference between these two motors, right? And the input in this direction will be the sum of all the torques with the sign for the opposite directions. So this assumes just the magnitude. That's why I put the minus here myself. All right? How do we calculate these forces and torques? Again, what I wrote on the board, it's proportional to the square of the velocities. And how do I transform these forces, these inputs, from the drone frame to the earth frame? I use the transformation matrix from the first slides, right? I don't put it here again, but you remember it. For the other configuration, similar things. Again, for the input or the force in this direction is the sum of all the lifting forces. Here it's a little bit more complex because I have all the motors rotating around this axis, having a torque around this axis, which is basically proportional to this length, which is square 2 over 2 times the length. Same story, nothing complicated here. All right? Let's try to build the dynamic model now, okay, that we understand how this thing flies and what are the inputs. Let's try to describe the dynamic model. Reminder of the notation: X, Y, Z translations on the earth frame, phi, theta, psi rotations on the earth frame, UVW velocity, and PQR angular velocity on the body frame, right? Xi translations, eta rotations, P linear velocities, rho angular velocities. Right. So how would we calculate the Lagrangian of this? What do we need to do? You remember the Lagrangian dynamic modeling?
We have Coriolis, the matrices basically.
Yeah. How did we end up with those matrices? How did we calculate them?
From the
potential and kinetic energy. So I need to calculate the potential and kinetic energies of all the links for robot arms, if you remember. I only have one body now, so things should be simpler. Right. Let's start with the easier one. Let's say, what's the potential energy of the drone? Sorry? mj has, or let's use z, because it's the up axis, the height axis on the earth frame, right? Which is the z, which is the position, the z position of the drone in the earth frame. All right? Anything else? Nothing else. This is it. Of course, this again is a simple model. It assumes no moving parts here on the up direction, which is pretty accurate. I mean, there's nothing moving internally. There's no deformations happening and whatnot. I mean, of course, if it crashes, but we don't talk about this. Right. Kinetic energy. We'll split in two parts. linear and angular. How would I describe the kinetic energy in the Earth frame for this one?
mv square.
mv square, 1 over 2. So again, I have the mass. V. What was the velocity of the drone in the Earth frame?
Velocity on Z. Because
All the velocities. That's in the robot frame.
The v it's
Xi dot. Because Xi is position, so I take the derivative of Xi. And because Xi is a vector, I have to write it in this form. Right? Transpose Xi. So I don't write square. Any other linear velocity? Nothing. I could go down to the level of the propeller spinning and try to model the kinetic and linear kinetic energy of the masses distributed here. That would be valid and it would be more accurate, but we're not going to do it now. But that would be basically one more thing to consider.
The way we control the individual movements, if the torques cancel each other out, do we need to model them?
Yes. What do we model here? What we try to model here? The inertia of the system. Right? What does the inertia mean? It's how much resistance does this physical system have to change? Change of position, change of angle, change of something, right? So if I want to be really accurate, I have to model the propeller spinning because these also have some resistance to spinning, because of the masses, right? They have some angular kinetic energy and also some linear one, but yes, they don't cancel each other out because the inertia only adds, right? These two, they might be spinning opposite, these two basically, but their inertia is not canceling each other out, right? It adds. Also, I'm not going there, whatever. So this is simple linear kinetic energy. It's usually good enough, but depends how accurate you want to be. If you want to do drone racing, maybe it's not enough. Like automatic, AI beating humans kind of drone racing. Maybe you can do a bit more effort and add one more thing. Maybe, if you really want to beat the humans. Okay. Good. Angular kinetic energy would be due to the rotations of the drone. So if you remember, we had again 1 over 2. Instead of masses, we had what? Moments of inertia. So we'll have, this thing has some moments of inertia, basically resistance to rotations. Eta. It's called. Eta dot. And I'll tell you one thing here. So the moments of inertia, if you remember, it was some matrix that was expressed on the frame of the link. In this case, it is expressed on the frame of the body of the robot, but since we describe everything in the Earth frame, I have to translate this to the Earth frame. If you remember how we did this for robot arms, it was with the transformation matrices. So this was B to E, and this would be B, E to B. That's how so this thing is basically that thing. And this is a function of eta. That's why this thing will be a function of eta. Right? This is not a function of eta. This is fixed numbers. Okay, but because we express the inertia in the Earth frame, which is fixed, and this thing rotates, obviously, it will have different inertia if I rotate around the z-axis when it's like this or when it's like this. And this is it. Again, I can go down to the level of modeling the inertia of the motors, of other things spinning, but we keep it here. Okay? So the total Lagrangian is this plus this minus this. I'm not going to write it here, I have it on the slides. expressed in the earth frame. Okay? Now, in order to get to the Coriolis matrices and so on, we had to do the Euler-Lagrange differentiation, okay, which was basically this one. So here I take the Lagrangian and I differentiate it with the derivative of p and with the p being combination of xi and eta, the coordinates of the system. Right, so you just write it in one. And if you remember, this was equal to the inputs of the system. I will eventually split it into the linear part and the angular part. So here I will have the derivatives with x will be equal to the linear part, and derivatives with eta will be to the angular part. So I will have basically this one. So I have the derivative of x dot and x equal to the linear part and eta. And we do this also because the system is pretty decoupled, right? Basically, these two only depend on xi. This is xi, right? So this is 0, 0, zeta being xi, or maybe better written xi times, let's write it like this. Okay, so that we only have the zeta part. Okay, so these are functions of xi, but they don't depend on the orientation at all. Like potential doesn't depend, if I mean, because it's basically we assume the center of gravity is at the axis, at the origin of the frame, right? And this one does not depend on xi. So the angular velocity does not depend where it is. It's the same angular kinetic energy, right? If I rotate with a certain velocity, whether I'm here or there, it's the same kinetic energy I will have. So it doesn't depend on xi. So I can basically split this in two subsystems and have the linear part, which I will derive with xi, and I will only have the linear velocity and potential being affected, because the derivative of this with xi will be 0 and xi dot, and the angular part will be only affected by eta and eta dot. All right. So this is my Lagrangian, and if I do the derivation with xi and xi dot, what will I have? Let's try to do it together before I show it there. Let's do it here. So what's the derivative of this with xi dot? This 1 over 2 m xi dot xi minus m g xi 0, 0, 1, whatever. The derivative with xi dot it will be 2 times, because this is kind of like a square. We did a derivation in the dynamic modeling part. Basically, this will end up with 2 times xi dot, right? This xi goes away, and the 1 over 2 goes away, and then this will be 0, right? And if I take the derivative of this with time, I'll basically add 1 more dot, so I get the acceleration. All right, and if I take the derivative of this with xi, here I don't have any xi, I shouldn't have any xi, so it will be just that part minus mg minus mg. Okay, so the first equation, this one will be this one minus this one, so it will be with a plus, I think. Yes, so I'll have basically this.
So when you do differential equations with vectors and tensors, it's more or less you differentiate line by line. Okay.
It's exactly that, not more or less.
Okay.
And on the slide before, it was written something. P in this case is the
V.
Okay, so it's
My bad. Yes, this is the potential. Sorry. I used to denote P, potential with P. I changed it, but I didn't change it here. Good point. Yeah, so this is V. Let's put it here so the people on the that follow us online on video can you hear us? All right. Good. So this is the first part, the linear part of the model, right? The second part is a little bit more complicated. Why? Let's try to differentiate this with eta dot. So I will have 1 over 2 eta dot eta, and then I want this derivative with eta dot. Sorry?
It is y of
There's what?
eta dot.
we consider the values of inertia to be not.
No, not yet. Later. Because it's a function of eta.
But if we differentiate,
With eta dot, yeah, it's not a function of eta dot. So yeah, how do we do it? So then it ends up being yeah, eta iota eta dot. I forget my Greek. It sounds like an American school. How do you call this? Alpha kappa c. Yes. All right. So this is okay. But what if we differentiate with time? That's the complication. Whatever. You can handle this stuff. The derivative of this with time.
So it's first the
It's not just a dot here. So it will be what?
time.
derived from time
Plus
plus
this derived with time. Which this in the end will be,
The derivative of two compound
yes, which will be basically this derived with eta times eta derived with time. So I will have, I can write it like, I'm not going to write it like this, but I could write it like eta with eta differential and then eta, and I will have a square here because the eta dot will go out. But we'll keep it like this for now. All right. Right. And what's the other derivation? So I have 1 over 2 eta dot t with eta. I didn't choose the notation, it's standard drawn notation, so I would have used something Latin, but whatever. So this will be the derivative of this with eta, whatever. We will call this, and in the lab I have the, actually no, this is not the whole Jacobian, so the whole Coriolis, but this is complicated to calculate. I have the full form of this on the lab. So basically, yeah, I have iota moments of inertia times acceleration of velocities of angles. Sorry, angular acceleration times this part that we said here, plus I don't even try to derive this, and eventually we sum these two together, and because these are the parts that depend on velocities, this will be basically my Coriolis matrix terms, right? So in the end, I end up with a similar system as with the drone manipulator, the arm manipulator. Well, I have an inertia matrix. It will be a function of eta now, and then I will have eta dot dot plus a Coriolis matrix plus gravity term based on eta equals to some inputs. Let's call it u. So it's the same form, right? The d1 will be what's with the second derivative. It will be the moment of inertia, and you see it's a function of eta dot dot, plus the Coriolis, which is a function of eta and eta velocity, and also from here. And the gravity term is this part. With a 0, 0, 1. So 0, 0 mg. Basically this one. Okay. It's the same form. Different derivation, but yeah, in the end we end up with the same thing. Okay. Now, this is the model. Let's talk a little bit about the inputs, because here we group them together as U linear, U angular. Basically, since we will take a simpler, not model, but a simpler use case where we will consider the drone basically hovering and moving slightly and not tilting too much, right? So in that case, I basically can ignore the lateral forces in a way. So the linear part, I don't have any forces in this direction. I just have the force up and down. And so this is in the earth frame, but I need to basically use the forces in the robot frame, because that's the ones I'm controlling with the motors, and figure out how do I convert this into the earth frame. It's with the transformation matrix that we saw in the beginning, the Euler angles one, right? So in the end, my first equation, this one here, if I replace for U linear what I have here, I will get this part. So it's again the mxc dot dot plus the gravity part on the right side. On the left side is the forces in the w direction transformed in the earth frame with the Euler matrix, right? So if I do these multiplications here, I will end up basically with equations for the accelerations in the three directions, x, y, and z, from this xc dot dot, right, equals to something relating to the w force in the w direction, plus, of course, some transformations. This tells me basically, okay, I have a w force, and I have some orientation, which is this cosinus, sinus is here. Okay, which direction will I move? Right, where will be my acceleration? X, Y, and Z, right? If you put all the angles to 0, you will see that I will go up and down. If you move this thing to, I don't know, by 90 degrees, you will see I'll go that way. In theory, I will not do it actually, but yeah. All right. For the angular part, it's a similar thing. I have the angular in the earth frame, the angular inputs in the earth frame. This has to be equal to what I calculated in the model. I have to add this thing here to transform to the earth frame. So I will have something like this if I invert it, because I want to solve for the angular accelerations here, right? Again, this is input in the earth frame. I need the input from the robot frame, so P, Q, R, so in the three axes of the frame. So again, I use the same orientation matrix. I didn't write the full form here because we're going to simplify soon. But I will basically have this as my dynamic model that tells me the acceleration. So this is the forward dynamics, right? I have as an output the accelerations in the 6 directions. And as an input, I have the inputs on the 6 directions, which are calculated based on the forces and torques generated by the motors that we saw earlier. Right, so this Ux, and this should be UW, UPQR. I'll go backwards. Are calculated here, right? Based on the forces generated, based on the velocities, and so on and so forth. All right. Now, this is highly nonlinear. I have nonlinearities here. I have cosinus, sinus everywhere. The Coriolis terms are also pretty nonlinear. So let's be engineers and simplify things a little bit. We said that we are going to consider basically the hover flight where we're just, tilting a little bit. So basically all this phi theta and psi, no, phi theta, not psi, phi and theta are very, very small. So when angles are very, very small, we can basically approximate cosinus of a small angle equal to 1 and sinus of a very small angle equal to that very small angle. That's the linearization that you probably have done before, right? And we consider all the velocities close to 0. Actually, eta dot is not all 0, phi and theta dot is 0, because I don't mind about this rotation. If you notice, psi rotation, if phi and theta are 0 or very close to 0, then psi will get cancelled out eventually. All right. Right. Actually, it doesn't cancel out, but it doesn't bother us. Right. So if I do this linearization, this approximation, and also I consider the upward force, this is just for convenience, so we never have to write mg anymore. I consider that in order to fly, I have to at least cancel the gravity. So my uz has always this gravity included. This is similar to the gravity compensation we did for robot arms. You can think of it like this. So I know what's the gravity, so I can always add enough force to counteract it. I can calculate basically this delta uz that I can, how much I need to influence so I go up and down. Whatever, this is just for convenience. So if I use this simplification, I end up basically with these equations here, which are a little bit more linear, right? So what do we see here? We see that the acceleration in the z direction will be basically proportional to this delta u, to the force that I have to add on top of gravity. Right? It makes sense. It's basically Newton's second law. M times acceleration equals the force. Okay. Then here I see that basically the angular acceleration around phi and theta will be proportional to the torque I give in those directions. Again, makes sense. And here I divide with mass. Here I divide with the moment, the part of the moments of inertia that plays there, like the x, for instance, or the y. So again, the inertia, some inertia around that axis. Right, and it's the same for psi. The interesting part is here, or at least what I find interesting, is that we see that in order to have some kind of acceleration in the x and y direction, I need to have some theta or phi angle. So if theta and phi are really 0, I will never have any translation, right? So the acceleration will be 0 on x if theta is 0. And theta is the rotation around y. So if this is x, this is y, I cannot translate, I cannot have acceleration in the x unless I have some rotation here. And the acceleration will be proportional to this angle. So the more I rotate, the more the acceleration, which from intuition we understand, right? But it's also on the equations. And it's the other way here. Here, in order to have acceleration on the y, I need to have a phi rotation.
And to have translation on x and y, do we mind if we also have an increase in height in z?
Depends on your trajectory. So what trajectory you want to follow. But you can keep it so that it doesn't increase in height.
If your drone flies into the ceiling, you mind or not?
I mean,
No, but you need an increase in height in order to keep the same altitude when you go left.
Compared to the, yes, I think you do. Yes, why?
Because when you change your angle of
And what happens?
attack, and now the thrust vector doesn't point perfectly.
Exactly. So when you rotate, your thrust vector looks like that, and your gravity still looks like that. So basically, if you want to counteract this gravity, you need to have a bigger vector here. All right?
So it's pretty easy actually to just have translation.
Easy. Just translation, but no height difference. Yeah, you can do it. You can do it, but yeah, you have to do all these calculations basically. All right, so that the force is balanced, this is the way you want them to balance, and so on. And on top of that, you need the controller, because if you just look at the forces, then it's going to be open loop. So you need to have some kind of feedback to see that you're doing what you're actually doing, which is the next step. So now we have the dynamic model, a simplified linearized model, okay, with some assumptions. Can we implement controller? And is it easy or not? It's not easy.
It's easy if we consider it only as a whole, as a one body, but if we take in calculations also for each wing, it's very difficult.
It's the other way around actually. Because we didn't consider these things, our control, our model is only representing the physical system in that limited range of motion, right? So we made some assumptions about all these things, and then our model is not accurate. Therefore, our controller will be good as long as these assumptions that we made are valid. Which means what? Yeah, that this inertia is not important enough, whatever, and that I actually don't tilt more, so that the linearization I did there is more or less okay, right? So we made several assumptions in the end to end up with a linear model, and I only told you half of them, and probably I only know a quarter of them of the assumptions. But yeah, some of the things I mentioned on the way, you can get an idea. Some things I didn't mention is like motor dynamics. Like when I send a signal to the motor, it doesn't immediately start spinning with the desired velocity, right? It has some delay. Delay in systems, it's not good. Yeah. We did talk a little bit about aerodynamics, but we didn't do like aerodynamic analysis of the whole drone. We just understood how propellers work. And even if you see propellers, they're not perfect. You can see these ones, they're a bit cut and so on. So they themselves, they don't really have, if all the motors manage to rotate in the same velocity, they will not all produce exactly the same force and torques. You can see the motors here and you'll understand why. And yeah, besides all these things, there's complication with the environment, we have disturbances, wind, and so on. And the final thing is that this thing is also under-actuated. Like physically, we have these limitations that we need to tilt in order to rotate. And I don't know if somebody tried to write controllers for these things, but yeah, the moment you start tilting, you break those assumptions we made about linearity, and it gets unstable. All right. However, even with a simple model, for simple motions, we can manage to fly them. Right. One example of a controller that we can implement, since we have a linear system now, we can apply linear control theory and do, state feedback, for instance, where our states are the positions and the velocities in the airframe. Actually, here it should be P, because it should be also the orientations, right? So it's all the, I'll close the door. Both positions and angles should be part of the states. And the inputs are the inputs at the drone frame, right? Upwards and the 3 rotations. If we write the model like this, basically starting from the dynamic model we define these are our states, we can write it in state space using, calculating the derivatives of the states, the accelerations basically, and how the inputs affect the accelerations. So if we have A and B, we can calculate state feedback gain. Maybe you remember one technique is pole placement or pole positioning. Our system has 12 states. So yeah, that's why I said it's not just Xi, because Xi is just the positions, but we have also the angles. So we have 3 positions, 3 angles, and then we have the velocities as well. So it's 12 states, and we have 4 inputs on the W, PQR. So in the end, our state feedback will be a gain of 12 by 4, or 4 by 12, sorry. And yeah, if we have the A and B matrices, we can calculate those based on some poles, and in the end, feed it back. So that will basically ensure stabilization. So it will not do anything. It will just ensure that the states of the system go all to 0. So 0 position, 0 angles and velocity. So basically not moving. All right. If we also want to follow a trajectory, we can add, an integration where it basically takes the current position, x, y, z, the reference minus the current position. So here we can have some trajectory generated, some reference for z, y, and x, and integrate the error between the positions and the references, and calculate with some gains inputs in these directions. So it could look something like this, where we have the model, the system, some state feedback here with a gain, just for stabilization, and then an outer loop where we get the position, the Xi, and we calculate the error based on a reference, we integrate the error, and we feed it, we add it together with the state feedback so that it follows the reference. This is what you will have to do in the lab after the holidays. Implement. We have basically the whole skeleton there. You have to calculate the gain matrix and implement the integrator. And you will see a small simulation of how the drone, basically you have to follow a circle. Not today, next week after the holidays. A very nice, but pretty much out of date by now, TED Talk on drone modeling. It's still nice, it's still very relevant, but yeah. You can see here, we still have to talk about great robots, next 2 lectures, so it's not complete yet, but you saw how we applied what we learned for robot manipulators in this kind of robots, and you can imagine what follows for mobile robots and underwater. Are there any questions? Yes, but
Can we design a controller only considering that the drone is a black box model? So we don't know anything from it besides what we get from the sensors.
so what else would we need to know? What do you mean black box? We don't know anything, no masses, no
Maybe
inertia.
That's it. And we have
Okay, what else did we consider here besides the mass and the moments of inertia? Not much, right?
yes.
We also considered, obviously, how the inputs affect the accelerations. Like, okay, the forces and the inputs that we give to the motors, how do they affect the states of the model in the end, right? So you need to have something about the model. If you don't know even that, then, I don't know. You will have to somehow have a process that you're trying to control. Otherwise, No. But in the end, you see, the only thing we consider is the mass and the moments of inertia.
More or less the question was if we can design a controller like with black box methods, like identification and so on.
Yes, but identification, I'm not an expert, but identification, you will start with at least an assumption about the model, right? At least you know something about the structure of the model. And then you're trying to identify some parameters of the model. So let's say, yeah, okay, you might not know the mass. And you can do experiments to estimate the mass. Or you might not know where is the center of the mass, because that's another parameter. It didn't appear in our calculations because we assumed the center of mass being in the center of the axis of rotation and everything being perfectly symmetric. But yeah, that's one thing, for instance, we didn't consider. What if the center of mass is not here and there? Then some calculation will change. But you need to have some assumption about the structure of the model so you can do system identification. You can try to do this fancy purely black box, I don't know, reinforcement learning kind of, control. I guess it might work, but the more you know about the model and you can feed in your whatever you're training, I think it always helps. You can try without.
Definitely. In the free time, this holiday.
Great. I'll let you present next time your findings. Okay. Have a nice week and a nice holiday if we don't see each other.